Hi students, hope you are doing well. Today we are starting lecture 74 in our aerospace engineering course, and today I'm going to introduce you to the topic of equilibrium equations. Specifically, these are equations which relate the different stresses which act on a given structure. I am Dr. Ranjan Ganguly. So let us again go back to the aircraft, consider this point, and at that point there is a certain stress state which acts there. Also, you know that at the same point there is also going to be a strain state which acts there, and these stress and strains are matrices, or you can think of them as vectors also. Now, we discussed a lot about the stress strain relation and so on, but today we are going to address the question, is there a relationship between the stress components themselves? Now, in my previous lecture, I showed you that there is something which relates the different strain components. So, let's say we take a plane elasticity problem where we have only three strains. So, we have epsilon xx, epsilon yy, and gamma xy. Now, what we can do is we can differentiate gamma xy with respect to x. So, I get this equation here. All I have done is differentiated both sides with respect to the x coordinate. Now let's say I differentiate this equation again, and this time I differentiate it with respect to y. So I get this equation here. Now here I can see that du by dx is going to be epsilon xx and dv by dy is going to be epsilon yy. So if I make the substitution in this equation here, the left hand side remains the same. Here I replace the du by dx by epsilon xx, so it becomes second derivative of epsilon xx with respect to second derivative with respect to y, and second derivative of epsilon yy with respect to x. So this is the equation known as the compatibility condition, which provides us the link between the different strains. So you can clearly see that the shear strain is related to the normal strain through this compatibility condition, and therefore if you are given a strain field which is a function of epsilon xx, epsilon yy, and gamma xy as functions of x, y, and z, then you can very easily figure out whether the compatibility condition is satisfied or not. Same thing if a displacement field is provided to you, that is u, v, and w as functions of x, y, and z, you can very easily calculate the strains and you can find if the compatibility condition is satisfied. Now this of course is the simple case of the plane stress, but you can easily imagine that this equation in three dimensions is also possible, and then you will get a set of equations like this. Now let's get back to stress. Now in our previous discussion we looked at stress at a point, and we had essentially looked at the case of uniform stress. So I showed you the different directions of the stress matrix, or the different components of the stress matrix. So if you remember, sigma xx is in this direction, sigma yy is in this direction, sigma zz is in this direction, and then there are all the shear stresses, for example tau xy, tau xc, and so on. Again, remember what I discussed at that point is that the way you get the shear stresses is that you take the plane where they act. For example, in this case they are going to act in the x is constant plane, so that gives us the tau x and tau x here. And the second part comes from the directionality. So this is acting in the z direction, this is acting in the y direction. So that's how we get tau xy and tau xz. And these are in the positive facing sides, or the side facing toward you, which I have made in red. The other sides act in the reverse direction because you need to have equilibrium in this particular condition. So this was a case of uniform stress, and there we saw that one of the conditions which comes out of uniform stress is that for moments to be satisfied, the shear strains have to be symmetric. So tau xy will be equal to tau yx, tau yz equals to tau zy, and tau xc equals to tau zx. Now today let's look at the non-uniform state of stress. So what happens here is that the body is such that on the sides which are facing you, which I have drawn in red, there is an additional change in the stresses. So here you can see the sigma xx has an additional component delta sigma xx. tau xz has an additional component delta tau xc, and tau xy has an additional component delta tau xy. Similarly, you can see here for the yy situation, there is the extra component delta sigma yy. Here for tau yx, there is an extra component delta tau yx, and there is a component delta tau yz. Similarly, here you have sigma zz plus delta sigma zz, and also you have a component tau xz plus delta tau xz, and tau zy plus delta tau zy. So what's happening here is that on the faces which are outward, the delta components are there, but the faces which are backward or inward facing, you do not have the delta component. So this is a non-uniform stress state where the stresses are changing along the directions of delta x, delta y, and delta z. Now for this body to be in equilibrium, I will have 6 equations. I will have 3 equations which tell us that the forces in the x, y, and z direction should sum to 0, and I would have 3 equations saying that the moments in the x, y, and z direction should also sum to 0. So let's start with the case of the first equation, that is sigma fx equal to 0. So what I will do is I will resolve all the forces in the x direction, and I will try to summarize them or sum them and set it equal to 0. So let's start with sigma xx plus delta sigma xx. This is multiplied by delta y into delta z. So that's the area of cross section of this face of the cube. Now the negative side is minus sigma xx delta y delta z, which is acting in this direction. Now next we look at tau zx plus delta tau zx. So that's the force here, tau zx plus delta tau zx, and this is multiplied in the direction delta x delta y. That's the area of cross section of this face here. So you subtract it from tau zx delta x delta y, which is in the reverse direction in this direction. Now the third force is that tau yx plus delta tau yx, and this force is in this direction here, and this has to be multiplied by delta x, this length, into delta z. So that's the cross section here which I have done here, and the negative side I get minus tau yx into delta x delta z. So this is the equation which tells me that delta fx equal to 0. Now what we do here is that we will immediately get a lot of cancellation. So you can see that the sigma x terms will cancel, the tau xc term will cancel, and the tau yx term will cancel, and I will only be left with the terms involving all the deltas. So I will get delta sigma xx into delta y delta z plus delta tau zx into delta y delta x, and delta tau yx into delta x delta z. This is all going to be equal to 0. So this second equation comes out of the first equation after cancellation of the terms involving the stresses. Here only the delta terms remain. Now once I have got this equation, I can divide this equation by delta x delta y delta z, and if I do that I get this more compact equation here. So for example, here delta y delta z is there, so if I divide it by all three, I get delta x at the bottom. Here I will get again delta x and delta y being there, I will get delta z at the bottom. Here delta x and delta z are there, so I will get delta y at the bottom. So I get this equation here. Now let's imagine a situation where this delta x, delta y, and delta z become smaller and smaller and smaller. So in the limit from calculus, they will approach the derivative. So what happens is now you are at a point. So at that particular point, this partial differential equation will hold, that is delta sigma xx by delta x plus delta tau xc or zx by delta z plus delta tau yx by delta y equal to 0. So that is the first equilibrium equation we have obtained corresponding to sigma fx equal to 0. So this equilibrium equation is nothing but this equation here, sigma fx equal to 0. It's expressed in the differential equation form. Now similarly you can do the algebra for the other two cases and you will get three equilibrium equations which are coming out of the force summation. So the force Fx, Fy and Fz are equal to 0 and I get three equations here. Now these equations look somewhat scary, but they are really not. If you look at it carefully, you will see in the denominator you have x, y, z in all these three cases. Here, for example, you have the first subscript of these stresses involve x, y, z, x, y, z, and x, y, z. And the second subscript in this equation is x. So there is x, x, x. Here it's y, 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 and here it's z, z, z. So that's one mnemonic to remember this equation by. You can remember this equilibrium equation if you want, but it's not something very difficult. It's kind of symmetric and straightforward. Now, as far as the moment equilibrium equations are concerned, they give you the same thing as we discussed in the past. If you try to do it out and see, you will get tau xy equals tau yx, tau yz equals tau zy, and tau xc is tau zx, which means that the stresses are symmetric. So this is something which we can even get from the equation for the uniform stress state. So let's summarize this important fact today. So now we see that when we have the stress matrix, there is a relationship between the stress matrix which needs to be satisfied if we assume that the stress is in an equilibrium condition. So these equilibrium equations must be satisfied by the stress field, and so the ones which involve the shear stresses are very straightforward. That means the stress matrix must be symmetric. But the ones which involve the normal stresses and the shear stresses, they are somewhat more complicated. So if you are given a particular stress field, you must ensure that the equilibrium conditions are being satisfied. So that's something which is required for equilibrium of the body. Now, if you are interested in further study of aerospace structures, this is a very deep field. We just gave a summary of some of the aspects here. Some of the things are without too much proof and so on. So you are going to realize a lot of information is there. For example, about the thin wall structures, about shear flow, about the various things which are there in torsion. There is the importance of transfer shear, warping is very important, and so on. And the particular type of monocoque, semi-monocoque, all that structures which are there in aerospace, you can study in detail in an aircraft structure class. So in that case, there are several books which I have found very useful. One of them is, of course, the Mechanics of Aircraft Structures by C.T. Sun. So that's a book I have used many times as a textbook. And there is also the aircraft structure book by T.H.G. Maxim. That was the book I used for studying when I was doing my bachelor's degree. There is also a particular book on strength of materials, which is a little bit advanced, but which is more amenable for the aerospace structures because it contains a lot of things about failure theory, warping, and so on. That's Advanced Strength and Applied Stress Analysis by Richard G. Budinas. So that's another book you can consult for more detailed information. For example, if you are interested in the complete compatibility equations with all the strains and so on, you can look at that particular book. And of course, remember there are many more failure criteria. There are failure criteria for brittle material, there are failure criteria for composite material, such as the Psi-Hill criteria, the Psi-Wu criteria, and so on. So those are studied in detail in separate courses in composite structure. So as far as most aerospace engineers are concerned, they have to take courses on vibration, they have to take courses in composite structures, and they have to take 2 to 3 courses in aircraft structures itself. So what we have discussed here is a very basic idea, so that again, as an introductory course, you now know some of the language and the vocabulary which is often used by aerospace engineers and aircraft engineers when they work in different companies, national labs, startups, or any such situation. And I will end this lecture now. Now next few videos we are going to start looking at propulsion. So we are going to first look at the propellers, then we are going to look at the jet engine, and then we are going to look at the rocket engine, the ramjet, and hypersonics, and then we are going to close the course. So I will see you in the next few lectures. See you then.